Okay, welcome to lecture. We'll get started here. And if you could just type into the chat box you're here for roll, that would be great. Okay, so we are talking chapter 2. We were finishing up on the last part of chapter 2, which we talked about electron configuration. We also talked a little bit about the periodic table there towards the end. So just to reiterate on the periodic table, so we have our periodic table, and we have group 1, group 2. Looks really crooked, huh? 3, 4, 5, 6, 7, and 8. So remember, our periodic table is broken up into really 3 parts. We have metals, we have nonmetals, and we have metalloids. And really right around here, right around where boron is in this area of the periodic table, there's sort of a staircase that comes down, usually on most of them that you could kind of see. And to the left there is where we find our metals. Above the staircase and to the right is where we find our nonmetals. And again, this sort of staircase is our metalloids. And remember that we have also over here on top of group 1 really is hydrogen, which is, again, a nonmetal, even though that it is hanging out with the metals in most cases. And we talk about groups that goes up and down on the periodic table. And again, really badly drawn here. Group 1 has a special name, which is the alkali earth metals. I'm sorry, alkali metals, not alkali earth metals, just the alkali metals. Group number 2 is the alkaline earth metals. There it is. When we go all the way across to group number 7, which is over here, that is our halogens. And group number 8 is our noble gases. Remember that we use the representative numbering when we number the periodic table. So that's 1, 2, and we skip this middle area here between group number 2 and group number 3. And then we go 3, 4, 5, 6, 7, and 8. And again, in this middle area between 2 and 3, these are our transition metals. And again, we also do have these 2 sort of periods or rows here at the bottom, which technically go right about here on the periodic table, and that's the lactonized and actinized series. And again, they follow those 2 elements on the periodic table. Remember, periods go on the periodic table left to right, and again, groups go kind of up and down on the periodic table. Any questions on the periodic table here? Again, you do need to know where everything's located: metals, nonmetals, metalloids, transition metals. You do need to know the names of those groups. So alkali metals, alkaline earth metals, the halogens, and the noble gases. All right, we also are still talking about electron configuration, and we can actually use sort of the periodic table to help us in electron configuration. So although we scribbled, I think, on the previous one here, it still sort of has some important information that we can look at. So here we have, when we look at the periodic table, the S's, and when we do electron configuration, if you remember, if you fill up all the S's with the electrons, that's 2 electrons. And on the periodic table, that is basically group 1 and group 2. So right here, group 1 and group 2, all the way up and down there in those groups, that's considered the S block on the periodic table. If you remember P subshell, you could put 6 in there, and that's from group 3 to group 8. So that's 1, 2, 3, 4, 5, and 6. So that's what's sometimes referred to as the P block on the periodic table. D subshells, if you remember, you could fill with 10, and that's right here in the transition metal region. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And lastly, if you remember Fs, you can fill with 14 if you fill them all up. And that's down here, and these two guys on the bottom, these are the F blocks, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 if you count them all the way across. You could actually use the periodic table here to do electron configuration, and the period numbers, all these period numbers, are the principal quantum numbers. So if you remember, n goes from 1 to 7, and so there's the periods here, and that's what you could do it. There's a couple things you do want to watch out for when you do it. Is we can do something, say, like sodium, which is right here. So that's sodium, which is 11. And we start up at the very top heading in this direction. So that would be 1s2 over here to helium, where it's at. 2s2 would take us to here. And then we would go all the way across 2p6 to the very end. And then we'd come down here to 3s1. So you could actually count off the electron configuration from the periodic table. There are a couple things you do have to watch out for. If you remember, the d orbitals start on the 3rd energy level, and that's right here, but that's actually on period number 4. So the d's are 1 behind the period number. So this is actually 3d, 4d, and so forth as you go down. The other thing is down here in our Fs. Our Fs actually start in the 4th energy level, and they're actually on period number 6. So they're actually 2 behind the period number. So this is 4F across going that way, and this would be 5F going that way as well. So you can kind of use the periodic table there to count off your electron configuration, and if you sort of know what you are doing. Again, there's a couple places where you can kind of go wrong. I personally would recommend probably still doing the zigzag approach. There you will be probably okay in terms of getting everything correctly. Any questions on that there? Okay. All right, so why don't you take a second here and write the electron configuration for each of these just to make sure. Then we'll talk about it. So take a minute or so, a couple minutes, and write those. You could do either one. You could do the short or the long version if you like. I'm going to probably do it not with the noble gas configuration. You could do it either way. Okay, let's take a look. Then we'll start with sulfur. So sulfur is number 16. So it's number 16 there. So that's going to give us 1s2, 2s2, 2p6. That's going to get us to 10. Then we're going to go 3s2, which is 12. After 3s, we then will go to 3p, and we need 4 in that case. So 1s2, 2s2, 2p6, 3s2, 3p4. Again, here, if you sort of use noble gas configuration, you would take this part of it, which is 10, and you would do neon in the brackets, and 3s2, 3p4 would be the way you could do that. Any questions on that one there? Next is barium. That's 56. Oh, that's a lot there. All right, let's go for it. So we got 1s2, 2s2, 2p6, 3s2, 3p6. Remember, after 3p6, it actually then goes to 4s2 after that. Again, that's that change that occurs. Then we actually go what we got there? 3d10 next, as it takes us all the way across the transition metals back to 4p6. And we're almost there, I think. So it's 4p6. Then we're going to actually go to 5s2. And again, after 5s2, we're going to go to 4d10. I got to move some stuff off my screen here so I have some room to write. So we got 4d10 takes us across there, and that's going to then take us to 5p6. And that then lastly should take us down to 6s2. Made it just in time there at the end of the screen. And obviously you could go back to what we got there. That is xenon before that, right? So you could just do xenon, which I think takes care of all of that, and have like 6s2. Any questions on that one there? All right, and lastly, we have chlorine, which is 17. So that looks just like the one above. 1s2, 2s2, 2p6, 3s2, and then we would go 3p5. Or again, you could do the neon. Any questions on how to write the electron configuration? This is obviously for some neutral stuff. We're going to talk about transition metals here and things with charges as well. Okay. So let's talk a little bit about some things with charges. First off, I don't know if we did last time or not, but just to make sure why we have this page here. So again, let's say we took our sulfur that had a -2 charge. And again, just to remind you that if it does have a charge, you do have to take into account the charge for the total electron sort of configuration. So sulfur normally has 16, but it would have 2 more electrons again for the -2. Minus means that it gained electrons. The 2 means that it gained 2 electrons. So you do have to adjust it So again, that does give you to 18, and that means that it would be 1s2, 2s2, 2p6, 3s2, 3p6 will get you there, and that would be argon's configuration. So again, if something has a minus charge, you do need to make sure that you adjust the electron configuration by adding the extra electrons into it. Again, with the positive guy as well. So if we had our potassium with we'll do calcium with a +2 charge. So calcium with no charge has 20. And when we have the +2 charge, we do need a -2 because of the charge that's here. Again, the positive means it lost electrons. The 2 means it lost 2 electrons, which would also get it to 18 and would be the exact same electron configuration as above. I think we might have talked about this just to refresh to make sure. Again, this is also argon. So as I think we mentioned last time, things that have the same electron configuration are isoelectronic with each other. And again, here in this particular example, sulfur with a -2, calcium with a +2, and argon, they all share the same electron configuration, and they're all said to be isoelectronic with each other. Again, here, as I might have mentioned as well last time, that that's really the whole basis of bonding, as we'll talk about in the next chapter as well. But the basis of bonding, especially for our representative elements, our elements in kind of group 1 through 8, they gain and they lose electrons, basically to achieve the same electron configuration as the noble gases. Noble gases are extremely stable; they're chemically inert, and that's sort of what everybody is trying to achieve in terms of their electron configuration. Through bonding, is to achieve that noble gas configuration. Any questions on charges, no charges for sort of our representative elements, electron configuration? Okay. So let's talk a little bit about transition metals. So transition metals are a little bit different in terms of sort of where they are and sort of sometimes their electron configuration. So our transition metals, again, are between groups number 2 and group 3, right on the periodic table. This is where we find our transition metals. And they have either completely filled or incompletely filled D subshells. And again, as we just saw earlier, that is essentially our D block on the periodic table. Again, starting with 3D where it begins. And there are some exceptions to the normal electron configuration in the transition metals. And 2 most common ones that we kind of look at or deal with is chromium and copper. And that's in the first period of the transition metals. So right about here, first row, transition metals are referred to on the periodic table. So chromium has 24 electrons and copper has 29 electrons. And if you follow, for example, for chromium, it has 24. If you follow that zigzag sort of configuration, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Now, the exception for chromium and also copper occur right here in the end. These orbitals, the 4s orbital and the 3d orbital, they're super close in terms of energy. They're very close in energy to each other where they're hanging out. And what happens, it's been found experimentally that both chromium and copper are more stable by kind of promoting one of those s electrons upward into the d orbital. So in the case of chromium, you can see we've sort of maximized our parallel spin, which was important, the way that those electrons go into the atom. So the exception is here. We have one more electron up in the D, one less electron up there in the S, and then that's how we get our 4s1, 3d5 at the end of the configuration because of that. Copper has a very similar exception. Again, if you did all that like you see down here, instead of that 4s2, 3d9, again at the end, like it shows, we have only one electron in the S, and an extra electron has come up. So in the case of copper, again, it has the one electron, but what it essentially will do then is pair off everybody up here. Another important thing about these sort of orbitals that are really important, especially what we're going to talk about next, which is sort of transition metals that gain charges as well, is actually what happens is when we look at these orbitals, the 4s and the 3d, this is the order in terms of filling. And as we talked about, that's how you should write your electron configuration. But actually what happens in reality in terms of energy is once electrons start going into the d orbitals, they actually switch in energy. There's actually a switch in energy. And what ends up happening after those d orbitals start to get some of those electrons is the s orbitals actually become higher in energy than the d orbitals. And that's going to be really important in terms of when electrons are lost, for example, in transition metals. So there's this switch that occurs in energy. And this is also why earlier as well, when we talked about it, that sometimes as you look in books or some other places, when people write electron configuration, you'll sometimes see electron configuration, again, almost written, in order. 3D, 4, and then 4P, almost in order, all the threes together, all the fours together. And again, when people do that, it's because of this situation here that there's that switch in energy. And this is, again, electron configuration written in terms of energy. And again, in this class and most classes that you do, you really don't write it that way. You write it in terms of filling, how the electrons go in. So again, that's why sometimes you'll see it in places and it's not necessarily technically wrong if it's written that way because it is based on energy, and that's probably why they wrote it that way. But I'll just put it this way. For our class, it'll technically be wrong. So you do need to write the electron configuration in terms of filling, not in terms of energy. Any questions on that? Now, in addition to chromium and copper, there's a lot of other exceptions to normal electron configuration. And it all occurs, actually, a lot of them do occur right there on the periodic table. If you look right below chromium and below copper on the periodic table in the transition metal region, there's a lot of exceptions, things like silver's exceptions. There's even some transition metals that have no electrons anymore in their s orbitals. They've all been promoted up to the d orbitals and so forth. But for our purposes, I'm going to say that these are the only two you need to worry about, chromium and copper. You need to worry about in terms of the exception to how they're normally written. Everybody else you could write based on the zigzag thing that we learned last time, even though, just so you know, and technically speaking, that might not be correct for a lot of them in the transition metal region. I think I might have a slide of those as well. Yeah. So again, this is just talking about the s orbitals and the d orbitals, how there's sort of a switch in energy. And here's a few more sort of examples of some exceptions to the electron configuration. And you could see that over here on the right-hand side are some of those exceptions. So for example, MO, RU, PD, when you get to palladium here, there's actually no electrons there in the S. They've all been promoted up to the D. So a lot of the sort of exceptions that you see in electron configuration are these S electrons kind of promoting themselves up into the d orbitals, again, just more for stability. And they're very easily able to do that because those two orbitals, the s orbital and the d orbitals, they're very close to one another in terms of energy to begin with. And even the more complicated it is, there's that switch in energy that basically occurs as it goes from one to the next. And the S's actually end up being higher in energy than your D's. So again, for us, you're responsible for chromium and copper. If you want to write the other ones like you see here on the screen, you can. There's actually more than just these here as well. So chromium and copper, you need to make sure you write the exception correctly. Again, others you could just write like normal. So let's talk a little bit about periodic trends there. And before we do, actually, let's talk about transition metals, though, and how they lose electrons before we go too far away from this transition metals here. So we'll just borrow this slide. So for example, let's talk about what happens when a transition metal will lose electrons. So let's take a look at iron, for example. And iron with no charge is 26, which means if we write the electron configuration for iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So that should be 26, I hope, right there. 10, 20, yep. So if something like iron gains a +2 charge, for example, iron with a +2 charge again means that it lost 2 electrons from its neutral, so it would have 24 electrons. And what will happen is, in this case, the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. And what's going to happen is, in transition metals, as we were just talking about, when they start to get those electrons in the d orbitals, there is a switch in terms of energy between these two guys. And what that ends up meaning is the 4s orbital is actually higher in energy than the 3d orbital. And that's important because electrons are lost from the highest energy level and then continue downward if they need more. So when something like iron loses the 2 electrons, the first electrons it's going to lose is actually the 4s electrons. And that would leave us a configuration of 3d6. So iron with a +2 charge would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Again, our 4s electrons are going to be lost first. Now, if we went to iron 3, iron 3 again would have 3 less electrons, which would take us to 23 electrons. Same deal is going to happen here. We're going to go 1s2, 2s2, 2p6, 3s2, 3p6. Same thing, we're going to lose our s electrons first, but in this particular case, that's only 2 electrons. So we still need to lose 1 more electron. At that point, the next highest electrons will be our Ds. So we would dip into our 3D and take away an electron, and we would end up with 3D5. Any questions on that? And this happens with all transition metals. So transition metals are slightly different when they gain a charge, become positively charged. Normal representative elements will lose the electrons, the last ones that you write in electron configuration, because those will be the highest energy levels, and they'll back up to the noble gases. Transition metals will always lose the s electrons first. So if they need to lose both of those s electrons, they'll lose them, and then they'll start losing d electrons as well. So why don't you try a couple here? Why don't you write cobalt with a +4 charge, and cobalt on the periodic table, neutral is 27. So cobalt is 27, no charge. And why don't you also do, why don't you do nickel with a +2 charge. And nickel with no charge on the periodic table, in case you don't have one in front of you, is 28. All right, so why don't you write the electron configuration for both of those, see what you come up with, and then we'll talk about it. Yeah, so what we're talking about now is sort of specific for just the transition metals. And because transition metals are metals, they pretty much will only make a positive charge, and they will always lose the s electrons first. And then again, if you need more electrons after that, then you go into the d's. The representative elements, like what we did with like sulfur and calcium, they typically will just lose or add to the very last guys in the electron configuration and end up at a noble gas. Okay, let's take a look and see. So we have cobalt with a +4 charge. So again, cobalt with no charge is 27. And if it has a +4 charge, that means that it lost 4 electrons. So that is 23, if I'm not mistaken. So you should be at 23. So we're going to do for cobalt with a +4, should be 1s2, 2s2, 2p6, 3s2, 3p6. And just to give you an idea where we're at, if we did cobalt with no charge, we are at, where are we at there? Argon. 4s2 and 3d7. So we're right here at the 4s2 at this point. And again, those are going to be the first ones that are going to be lost. So we're going to lose those 2 electrons there. That's only 2 electrons. We do need to lose 4. So we are going to take 2 out of here, and that's going to get us to 3d5 in that particular case. Any questions on that there? Same thing if we kind of look at our nickel with a +2 charge, going to go to 26. Again, our nickel with no charge would be argon 4s2, 3d8. So here, again, we're going to actually lose those 2 electrons from there, and that would get us a nickel. That is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d8 in this particular case. So again, transition metals always going to lose those s's, then into the d's if necessary, or in this case, as you can see, not necessary to dip into the d's. But again, those representative elements will always add or gain to the last guys in the electron configuration, and again end up as noble gases. Uh, let me look at your question real quick here. So if your question is, do the transition metals always lose the 4s electrons first? The answer is yes. Now, again, there are some in their kind of neutral state transition metals that will have some of their 4s electrons transferred to the d orbitals, but not every single transition metal will do that. So just like the ones on the screen, for example, are some examples of those when they don't have a charge, have some of them that have been found to be more stable in that configuration with an extra electron in the d, one less electron in the S. But what all of them will do is, in terms of transition metals, when they start to lose electrons, and again, transition metals are metals, so they will always lose electrons. When they start to lose electrons, they will always lose the S's first and then into the D's. Yeah, so it worked the same way. That's a good question about chromium and copper. So for example, let's say we had copper 1, or we'll do copper 2. Let's say we had copper 2, for example. Now, copper again is 29 with our no charge, right? And its correct configuration is right here. And when copper has a +2 charge, again, that's going to take it to 27, right? So you would do the same approach here if this is your question. We're going to lose our S electron first, but in this case, it only does have the one electron to be lost. So we would lose this electron, but then we would have to obviously delve into there to get to our next electron. So it would end up with something like argon 3d9. So in terms of those exceptions, it does still follow the same sort of approach. The only difference is in those exceptions, they don't have 2 electrons in the s orbital. They only have obviously 1. So you would only lose 1 first and then go into the d. Other questions on transition metals and electron configuration? Obviously, something like palladium down here, you would start with the d since it has no s's to begin with as well. Any other questions on that? Okay, then let's talk a little bit then here about some periodic trends. And we're going to talk about a few of these different periodic trends here. We're actually maybe going to add one to it, which is electronegativity as well. So we're talking about ionization energy, electron affinity. We're talking about the atomic radius and electronegativity. And we're going to see with all these trends why we see certain things occur with metals and certain things occur with perhaps non-metals in terms of what happens in terms of gaining or losing electrons. So let's talk about each of these here. The first thing is ionization energy. And ionization energy is the energy that's required to remove an electron from the gas phase of an atom. So the ionization energy is that energy that you need basically to remove an electron. And when we do remove an electron, as we may know, when we remove an electron, we make a cation, so something becomes positively charged. So ionization energy occurs when we remove an electron, and that's going to result in a cation being formed, which is positively charged. And the ionization energy, in terms of general, as we will see when we look at the periodic table, it increases as you go this way, and it decreases as you go down on the periodic table. So the ionization energy up and to the right on the periodic table will increase. And what that means is as you go up and to the right, it takes more energy to remove an electron from an atom. And it decreases as you go left and down. And again, what that means is it doesn't take as much energy to remove an electron. Now, electrons actually do come off one at a time. So after, say, the first electron comes off, that's what's referred to as the first ionization energy. When the second electron comes off, then that is the second ionization energy. The third ionization energy is when the third electron comes off. So again, they do come off one at a time, and that's what's shown here. So magnesium with no charge, the first thing that will happen is it will lose an electron. And that is what is referred to as the first ionization energy for magnesium. And in this particular case, it's like 735 kilojoules. Then what will happen is the magnesium that has now lost one electron and has a +1 charge will then lose a second electron and become -2. And this is what will be referred to as the second ionization energy. And that's the energy to remove that second electron. And you should be able to kind of see a pattern here. It is much easier to remove the first electron than the second. And that's because in a neutral atom, everybody is out by themselves with those electrons. But as soon as you lose an electron, all the electron density basically gets smaller. So everything comes in, and all those electrons that were originally further away from the nucleus now find themselves closer to the nucleus and being held a lot tighter. And we see that as a result here in the energy difference as we go from our first ionization energy to our second. There's almost a double increase in terms of the amount of energy required to remove that second electron. Then what possibly could happen is the magnesium would then lose perhaps a third electron and become with a +3 charge. And you can see the incredible jump in energy as we go from the second to the third electron. And that actually doesn't happen for something like magnesium. And that's because we get into what is referred to as the core electrons. So there's really two types of electrons. So if we write the electron configuration for magnesium, it's 1s2, 2s2, 2p6, 3s2. The electrons in the highest energy level, which would be these are what are known as valence electrons. They're the highest energy level. They're also further from the nucleus as well. So your valence electrons are your highest, most energy electrons. They are furthest away from the nucleus. Also means that they're not going to be held as tightly, right? They're so far away from the nucleus that they don't really feel the full brunt of that positive charge from the nucleus. So they're just kind of hanging on there, and they're not being held super strong, and they're able to be lost really well. When we go below those guys, these guys are what are referred to as core electrons. And core electrons are electrons that are actually lower in energy, which means that they're closer to the nucleus and they're going to be held a lot tighter. So when we look at something like magnesium, the first two electrons, not really a problem. They could come off. But then you try to rip off one of these electrons down here, it's really not going to happen because they are too close to the nucleus at that point. Again, remember, after the first electron basically comes out, it gets smaller, and then the next one, it gets even smaller. And so those electrons, by the time you try to take that third electron away, those electrons are very, very close to the nucleus at this point, and are going to be held extremely strong and not going to be able to remove. And that's why something like magnesium will typically only make a +2 charge. So a couple of things while we're here talking about this, and let me see if maybe we got a better spot here. So in general, as we go across a period from left to right, the first ionization energy will increase. And again, electrons are being added. So let's just talk a little about sort of that little aspect of the periodic table here. So we had group 1, group 2, 3, 4, 5, 6, 7, and 8. So a couple of things about periodic table which will help us understand some of the things that we see here. First off, to figure out the valence electrons, for example, you could just write out the electron configuration and find which electrons are the highest in energy. But the number of valence electrons equals the group number, especially for the representative elements. So guys in group 1 all have 1 valence electron. Group 2 would have 2 valence electrons and so forth. Group 3 will have 3, 4, 5, 6, 7, and 8. So when we were looking at our magnesium, there's group number 2. It has 2 valence electrons. In addition, on the periodic table, there are certain things that will make sort of fixed charges. So everybody in group 1 will make a +1 charge no matter what the situation is. Everybody in group number 2, when they do make a charge, will be +2. Everybody in group 3, which is usually aluminum here, we're talking about, will be a +3 charge. And again, this is about where that staircase comes down. We skip group 4 and group 5, the nonmetals, which is above that staircase, when they do make a charge, will be -3, -2 for our group 6, and -1 for our group 7. So the transition metals, as you may know, and as we'll talk about, can have a variety of charges. So they really don't have fixed charges, but there are still 3 actually in the transition metal region that does have a fixed charge, and that is zinc and cadmium. So right about here, zinc and cadmium. Even though they're transition metals, no matter what the situation is, they will always form a +2 charge when they do form a charge. And if you hang a left at cadmium and go to silver, silver will always form a +1 charge. So a couple of things about charges, just to make sure everybody, again, is on the same page. As we've talked a little bit about here a couple of times, metals are the guys that will form our cations and become positively charged. Nonmetals, which is upper right of the periodic table, will form our anions and become negatively charged. Again, metals losing electrons and becoming positively charged, nonmetals gaining electrons, becoming negatively charged. So when we look, though, at an element on the periodic table, just so we're clear, if you have the element all by itself, not combined with anything else, it does not have a charge. So sometimes people think things always have a charge, but they don't. So again, if you had something like sodium metal, it would be sodium with no charge. Sodium would only gain a charge when it hooks up with like a nonmetal. So really, metals and nonmetals only really gain charges when they actually come together and combine. If they're by themselves, they have no charge. So if you had sodium metal, it would just be Na solid, no charge. If you had sodium as part of something like sodium chloride, it would be sodium with a +1 charge. Again, not by itself. It's combined with a nonmetal. That's when it really will get that charge. Same thing with nonmetals. If you had chlorine by itself, no charge. It'd be Cl2. Remember, that's one of those diatomic molecules. But again, if you had the chlorine in with the sodium, this would have a -1 charge. So important to remember, sometimes people always think, oh, things always have the charges, and they always have charges. But again, will only have charges when they really combine with something. If they are by themselves, you just took it straight off the periodic table, nobody has a charge. Also, you should remember, as well as we talked about hydrogen here, which is on most periodic tables. Again, as we talked about last time, not part of group 1. Also, it is a non-metal, not a metal, right? And again, hydrogen by itself comes as H2, right? Also no charge associated with it. That's how it naturally comes. Hydrogen, as well as we'll talk about, actually can do both things. It could be a +1 charge. Hydrogen also can be a -1 charge. So it could actually go both ways, which is why hydrogen is sort of in some interesting locations on the periodic table. So when we think about just charges and just looking at this periodic table here that I sort of drew, we see that as we go up and to the right on the periodic table, our ionization energy increases, which means it's much, much harder to remove an electron as we get up into our non-metal region up in this case. And that's why when we look at the charges that occur for our nonmetals, they actually become negatively charged, which means instead of losing electrons, they most likely like to gain electrons. And that's different if you think about all of our metals over here in this region, right? All the way across all of our metals. The metals essentially become positively charged. So if you think about where they're located on the periodic table, they're located to the left and down, and that's where ionization energy is less. And that's because it doesn't take a lot of energy to remove an electron, which means it's relatively easier to remove an electron from a metal, and that's why they typically become positively charged. So 2 things with ionization energy. Definition is the energy required to remove an electron from the gas phase. It increases as you go up and to the right on the periodic table, decreases as you go left and down, and it takes, the electrons do come off one at a time. So there's the first ionization energy for the first electron, second for the second electron, third ionization energy for the third electron, and so forth. But the pattern that we see in terms of first versus second versus third ionization energy is the amount of energy increases as you go from the first ionization energy to the second ionization energy to the third, as we see here on this slide. As we keep trying to remove those electrons, it takes more and more energy. And at some point, you will reach pretty much your core electrons, and you probably won't be able to remove those electrons at that point. Any questions on that there? All right. So again, I would probably cover some of this, but in general, as we go down a group from top to bottom, the first ionization energy increases. And some of this has to do with actually size as well. So let's talk a little bit about that as well. And if we look at the periodic table, and we talk about atomic size, as we go left to right on the periodic table and up, size gets smaller. And as we go down and to the left on the periodic table, the atomic size gets larger. So if you think about an atom and sort of where electrons are, as we go, excuse me, as we go up and to the right on the periodic table, the overall size of that atom is much smaller, which means the overall size of that atom is much smaller. That also means that because overall it's much smaller, the outer electrons, even though they're furthest away from the nucleus, are still going to be closer to the nucleus because the overall size is smaller. And that means it's going to be a lot harder to remove those electrons because they are closer to the nucleus. As opposed to if you go to the left and down, the overall size of the molecule is larger, which means those outer electrons are further away from the nucleus. They're not being held as tightly by that nucleus, and they're easier to remove. So atomic size is really important, even though we're still dealing with sort of valence electrons, those outermost highest energy electrons. When we go up and right on the periodic table, even though they're furthest away from the nucleus, because the overall size is smaller, they're going to be held tighter and take more energy. And that's also because, again, if you look at the periodic table, as you go to the right, in terms of protons, you're building up your protons, right? The atomic number increases on the periodic table as you go to the right, which means as the atomic number increases, so does the number of protons, right, in your nucleus, which means as you go to the right, you are getting a lot more protons, a bigger positive charge, and that bigger positive charge are going to bring those electrons closer to the nucleus. And again, as they get closer to the nucleus, they're going to be held tighter and require a lot more energy to remove them. And again, that's opposite. Again, if you are to the left on the periodic table, let's draw it like this. The positive charge is not so big there in the nucleus, as we don't have as many protons. So again, those electrons are not going to be pulled as close to the nucleus. So they're going to be out a little bit farther. And again, because they're a little bit further from the nucleus, they're not going to be held as tightly, and it takes less energy to remove them, which is essentially what that should say. So here is the values for the first ionization energy for the first 6 periods. And we do see that trend as we go down a group. For example, this is group 8. You can see that the ionization energy decreases as you go down group 8. This is group 7 over here, fluorine, chlorine, and so forth, heading in that direction. And again, you can see it starts to decrease as you go down a group, or opposite of that. If you look at it, it increases as you go up the group. So explain why the graph for ionization energy versus atomic number is not linear. Again, we do have electrons near electrons. So they are going to be repulsed by each other. So that does play into effect in terms of ionization energy. And there are some exceptions, and you don't have to worry too much about this. But what we're talking about is, let's talk about also another very important sort of aspect of this idea. And this is what is sometimes referred to as shielding and effective nuclear charge. So the idea, for example, of shielding an effective nuclear charge. So let's say we took a nucleus that had a +3 charge, right? And by the way, that would be lithium. And if we had 2 electrons on a lower energy level and an electron on a higher energy level there. So this would be more like our valence electrons. These guys would be more like our core electrons, closer to the nucleus. So when we think about this electron out here, this electron out here does not feel the full brunt of that positive charge. And that's because he is shielded from those charges by these lower energy electrons. As opposed to these core electrons, they're right on top of that +3 charge, so they feel like that +3 charge. So these core electrons, they tend to feel like that +3 attraction. And when we talk about positive and negative attraction, the strength of that increases with the charge. So something that's like a +3 plus a +3 -3 sort of charge, they are attracted to each other and held stronger than, say, a +2 and a -2, or a +1 and a -1. So the degree of the charge actually affects how strong that attraction will be. So these electrons in the core area feel the full brunt of that +3 charge, which is going to hold them there pretty tightly. But when we get to our valence electron, he feels what is sometimes referred to as the effective nuclear charge. And that is the atomic number minus the number of shielding electrons. So in this case, the atomic number is +3. Our positive charge is +3. And in the case of that valence electron, there's 1 and 2 electrons in its way. Which means for the electron that is way out there in the valence area, instead of feeling that +3 charge from the nucleus, what it actually feels is more a +1 charge. And that means it's not going to be held as tightly. It's only feeling like a little +1 charge. So it's able to be lost a lot easier than those core electrons, which are right on top of it, and it feels a +3 hold on those electrons, and they're not going to be able to go very much or very far. So effective nuclear charge is really the positive charge that an electron sort of feels as a result of shielding. So it's kind of like when you go to the movie theater years ago before they assigned seats. You used to get there early. You get that nice center seat right in front of the screen. And then right before the movie starts, some guy comes and sits with a big giant hat, right? Blocks out half of the screen. So he's kind of shielding you from the screen, the full effect of the screen. And that's sort of the same idea that happens with electrons. Because those lower electrons are closer to the nucleus, they sort of block that positive charge that the outer electrons, those valence electrons, feel. And that's why valence electrons really are the electrons that are involved in bonding. They're the ones that are lost in the sense because they're not being held as tightly. So effective nuclear charge, again, is sort of the positive charge that an electron in the outer levels would feel as a result of the lower core electron screening out or shielding it from the full effect of the positive charge from the nucleus. So let's talk a little bit about which atom we would, excuse me, would require more energy to remove an electron, sodium or chlorine. So when we look at sodium, chlorine, they are in the same period on the periodic table. And we see that chlorine is further to the right on the periodic table. That means that chlorine should have a higher ionization energy and should hopefully require more energy to remove an electron. And that's again why sodium will typically not lose an electron but gain an electron and become negatively charged, while the sodium will be the one in this sort of situation that will become positively charged and lose an electron. Which atom will require more energy to remove an electron? This is lithium and cesium. They are in the same group. So we'll draw it like it is on the periodic table. So again, cesium is lower in that group, which means again it's to the left and down. It should have less or lower ionization energy, which means it should require more energy to remove an electron from lithium in this particular case because of that. Which has the larger second ionization energy and why? So this is lithium and beryllium. So lithium is group 1, right, on the periodic table. Beryllium is group number 2, right? And the one that would have the larger second ionization energy, so the key here is second ionization energy, that is the energy to remove the second electron, which means you're going to turn that thing into a +2 charge is what that means. And the answer should be lithium. And the answer is lithium because lithium is 1s2, 2s1, while beryllium is 1s2, 2s2. And in this particular case, once lithium loses the first electron and becomes positively 1 charge, the only thing left for lithium now is its core electrons, right? And as we talked about, that is when you get into a ridiculous amount of energy needed to remove an electron, and it becomes much, much harder. While beryllium, which is group 2, remember everybody in group 2 +2, right? Which means these are its valence electrons. And this is its core electrons. So if you want to get to the second ionization energy, you could remove 1 and 2 electrons here with no problem because the second electron that comes off will still be a valence electron. And that means that it doesn't take as much energy as opposed to lithium, where the second electron would be that core electron. And that's why lithium you will never see with a +2 charge because again, you would be delving into those core electrons and it would take too much energy to remove those. Any questions on that? And here's a table that describes the first, second, third. So this is all the different ionization energies as you go here. So basically this is the first electron that comes off, the second electron, third electron, fourth electron, fifth electron, sixth electron, and so forth. And again here, sodium, which is group 1, it makes a +1 charge, and you can see the tremendous jump. If you would try to remove that second electron, again, you're getting into core electrons, almost a 10-fold increase in the amount of energy that's required, and again, does not happen under normal conditions. Here's our magnesium, which usually makes a +2 charge. So that much energy for the first electron, double it for the second, but then again here, you're getting into like 5 times more energy if you try to remove that third electron. Not going to happen. Aluminum, which is group 3, typically will make a +3 charge. Not too bad here. Gets a little bit harder here as we get to the second, a little bit more. But then as you try to remove that fourth electron, you can see the tremendous jump in energy required to do that. Again, doesn't happen for something like aluminum. And that's why aluminum only gets to +3, because once you get to that for aluminum, (3p1). This is the 3 valence electrons. They're all in the third energy level. But once you try to get to that fourth electron, you're down there in the core electrons at that point. Not going to happen. So again, the general trend is increases to the right, decreases down. But again, once you start getting into those core electrons, they don't typically get lost. You will not have to know the exact numbers for anybody or anything like that. What you need to know in terms of ionization energy is obviously what it is and the general trend on the periodic table as you go left to right and up and down. And you also need to know that as you go from the first ionization energy to the second ionization energy to the third, that it does increase as well. So as we see here on this chart, as we go from the first to the second to the third for an element, as you continue to remove each of those electrons one at a time, the amount of energy required to remove them gets higher and higher as you go through it. Other questions? Okay, so let's talk a little bit about electron affinity. And as we were just talking about with ionization energy, that's really the energy required to lose an electron or make a cation. Now, electron affinity, when you have an affinity for something, that means you usually like it, you're attracted to it, is the energy change that occurs when an electron is gained by an atom. So ionization energy, you could kind of think about it as the energy that describes what happens when we make a cation. Electron affinity is essentially the energy change that occurs when we make an anion or something that is negative. Okay, yep. So right here is the gaining of electrons is basically what we're talking about right here. So the electron affinity is, again, that sort of energy change that occurs as electrons are actually gained by an atom. And in general, electron affinity on the periodic table increases as we go this way and decreases as you go down. Unlike ionization energy, it's not like really perfect, if you will, in terms of going up and to the right or going down, but that's sort of the general trend in electron affinity is up and to the right, it increases, down and to the left, up and to the right, it increases, down to the left, it decreases. And again, that's the energy change as we go that way. Usually the more negative or increase in negative in terms of energy as you do that results in a higher electron affinity. And not perfect. So for example, group 7, if you looked at electron affinity in group 7 of the periodic table, it does increase, and then it goes down a little bit as you get to the top. But the general trend is that it does sort of increase as you go up a group and to the right. So ionization energy, kind of for making of a cation, negatively charged. Electron affinity is sort of what we associate with making an anion or something that gains electrons. Atomic radius, as I talked about as well, is again, as we go left to right on the periodic table, gets smaller up and to the right. And as we go left and down on the periodic table, it gets larger. Again, for what we were talking about with the effective nuclear charge and so forth. And sort of that build-up principle, again, periodic table up to the right, or just to the right in general, you're building up more and more positive charge. So that's why overall, everybody on the right-hand side of the periodic table is much smaller, because all those positive charges in the nucleus brings all those electrons closer in, as opposed to when you go to the left, there's less protons. Again, those electrons going to be further away from the nucleus. So here's a picture of that, and we can see as we go to the right, it definitely gets smaller, and as we go to the left, it gets larger. Let's also talk to why we're here about ions. So again, if we have a cation, which is positively charged, versus a neutral atom. In terms of the cation versus the neutral atom, when it loses electrons, typically the cation will become smaller than the neutral ion. Again, it lost electrons, so it lost a lot of its electron density around the outside. So the whole atom just shrinks as it loses those electrons. And versus an anion, which is negatively charged, versus a neutral atom. When we do a negative guy, the negative guy becomes larger than the neutral atom. And again, the idea behind that is as it gains those electrons, the overall cloud gets larger, right? So it starts here, gains some electrons, electron cloud gets larger, it starts to increase as well. So in terms of anions, if it's positively charged, we see a overall size decrease between the positively charged ion and its neutral counterpart. And when we have a negatively charged ion, it becomes larger or more positive, or larger in size, because it gains more electrons than its neutral atom. So which should be a larger atom, sodium or chlorine? In this case, sodium is further to the left on the periodic table. So sodium should be larger. Which should be a larger atom here. Again, lithium and cesium in the same group. So size increases as we go down a group. So the cesium should be larger. Which is larger, the hydrogen 1s, the hydrogen 1s orbital or the lithium 1s orbital. So in terms of size, the lithium should be larger, again, is further down in the group on the periodic table. And which one should be lower in energy? Lower in energy, again, would be the hydrogen, as is closer to the nucleus. So we want to arrange these in terms of order between oxygen, fluorine, and sulfur. So oxygen, fluorine, and sulfur. If we look on the periodic table, they are arranged like so. So sulfur, oxygen, and fluorine. So in terms of ionization energy, again, ionization energy increases as you go this way and decreases as you go this way. So we would expect fluorine to be the highest in ionization energy, followed by oxygen and then sulfur. So we want to go in increasing order. So it should be sulfur, oxygen, and fluorine in increasing order. So it should increase and increase this way. Atomic size will be, again, if we look at atomic size, smaller as we go this way, larger as we go this way on the periodic table. So if we want increasing size, we would actually be going this way, right? Gets larger that way and larger that way. So it should be FOS in this case. Any questions on that? Now, let's see here. So the number and type of valence electrons are primarily determined by the atom's chemistry. Again, electron configuration can be determined from the periodic table, the way it's organized. Again, certain groups, as we talked about, have special names. Here's a much prettier sort of illustration here of the periodic table. Again, we have our alkali metals, which is our group 1, our alkaline earth metals, which is our group 2, our halogens, and our noble gases, as we talked about. But let's talk a little bit about these trends and sort of how it relates to our periodic table. Let me just see if I have one more picture. I do, I think, yeah. Okay. And we'll go this way with it, I think, here. So the last sort of trend that you do need to know about the periodic table is electronegativity. And electronegativity is actually found in chapter 3. So this is the only thing from chapter 3 that you need to know for exam 1. And electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, it increases as you go up and to the right, and it decreases as you go left and down. Fluorine is the most electronegative. So when we put electronegativity in with all of our trends, so if we look at the periodic table here, in terms of ionization energy, it increases as you go up and to the right and decreases as you come down. In terms of size, it gets smaller as you go up and to the left, up and to the right, and gets larger as you go left and down. In terms of electron affinity, increases as you go up and to the right, decreases as you go down. And lastly, if we add our electronegativity in there, increases as you go up and to the right and decreases as you go down. Electronegativity, again, is the ability of an atom to bring electrons towards itself. It is actually different than electron affinity, which is the energy change that occurs within an atom when it gains an electron. But what all these things tell us is as we go up and to the right on the periodic table, those are guys that are smaller, they hold on to their electrons, and they want to gain electrons. So all that makes us know that when we go this way on the periodic table, where our nonmetals are, those are essentially guys that want to gain electrons. And that's why nonmetals are typically negatively charged. And all these trends, when we go to the left and down on the periodic table, everything is larger, which means the electrons aren't held as tightly. It doesn't take a lot of energy to remove an electron, and they really don't have much of an interest in hanging onto their electrons. Tells us as we come to our metals, they are the guys that will become positively charged and cations and will lose electrons. So all these trends lead us to what we sort of know, which is nonmetals gain electrons and become negatively charged. Metals lose electrons and become positively charged. Any questions on that? Okay, I know we're kind of a little over. We're just going to go a little bit over just to finish this because there's much prettier slides than what we saw earlier, just to reiterate the periodic table and where everything is, which is a much better slide. And we'll start lab just a little bit later today, just to compensate here. So let's just go take a look at that. So here's, again, a much prettier picture than those really badly drawn periodic tables I did earlier, just again, so you can see it. But again, you do need to know your groups, which way they go, 1, 2, 3, 4, 5, 6, 7, 8, again, using the representative groups. And again, the names of those groups, the alkali metals, which is group 1, as you can see there, starts with lithium. Again, not hydrogen, even though it's there. Alkaline earth metals, the halogens, and the noble gases. There's our transition metals, as you can see here. And again, our lanthanides and actinides, which again go, kind of in this region of the periodic table. Here are the break apart of the different groups that we talked about. So all these guys over here are metals. Again, a reminder that hydrogen, which is this guy, is a nonmetal. And obviously all of our nonmetals are over here. These lanthanides and actinides, which again go in here, they are obviously metals as well. So they technically would go here. These are our metalloids here coming down on the periodic table. That's what we were referring to as our staircase, as you could kind of see there, as I keep drawing lines all over it there. But that is our metalloids. So those guys in the bluish area are metalloids. I kind of went a little over. That's aluminum. It's not a metalloid. But some books will include boron in there and some books won't. I think your book doesn't include boron as a metalloid. But the metalloids, again, are semi-metals, which are sometimes referred to. And again, they have properties that fall both as metals and non-metals. So they have very similar properties that are there. So obviously, as we talked about before, you need to know where metals are, you need to know where non-metals are, and you need to obviously know where the metalloids are as well. There you go, trying to erase some of that there. So again, our metalloids here. All right, and let's see. The alkali metals, as we talked about, they're very reactive. Again, for some of those trends that we talked about, they're the most chemically reactive metals. Again, they're found furthest to the left on the periodic table. Going down the group, again, ionization energy decreases, the radius increases, and the density also increases as well. Melting and boiling points happen too. So just to look at the periodic table here in terms of the trends that we were talking about, the most active metal would be found in this area, right? Most active metal. Again, because that is as far to the left and down you could go. That is as big as you could get and not as much ionization energy and stuff like that. And then obviously upper right over here, most active non-metal would be found. Again, for the opposite reason, that's sort of as far to the right as you could go, and you have all those trends working together. Any questions on any of that? I think that should be chapter 2, if I'm not mistaken. Yep. That should be it, I believe. Yep. Any questions on chapter 2? So reminder, that should be everything that's going to be on exam number 1, which is 1 week from today. And it will cover chapter 1, it will cover chapter 2, and from chapter 3, it will basically cover electronegativity. So for exam 1, you just need to know what electronegativity is from chapter 3, and you need to know the trend on the periodic table in terms of electronegativity. When we get into chapter 3, which is next, we will get into really chapter 3 in terms of bonding and stuff like that. But for the first exam, that's all you need to know is kind of what electronegativity is and the trend. Any questions on any of that stuff there? We will not be doing probably a test review or anything like that, to be honest with you. We're just going to continue lecturing and stuff like that. But again, as I mentioned last time, sometime this week, there will be kind of a sample sort of quiz or something like that you could do with the proctoring program, again, before next week, so you could get an idea as to how that all works as well. Any other questions on that? Okay, so we ran a little bit over. So why don't we start lab? About 9:55. We'll start about 10 minutes late since we went a little bit over about that. So we'll start about 9:55 for lab. We're going to do experiment number 3 today, which we kind of postponed to today. We'll talk about it, and then obviously could go and do the lab and all that good stuff. Any other questions or anything like that before we call it a day for lecture? Okay, I'll see everybody in about 20 minutes. So make sure you come through the lab link, and we will go that way. If you didn't type in here for roll, make sure you do so. And I'll see everybody in about 20.